Hello, welcome back, and today we are going to take a look at BERT. So as you can see, I have a picture of BERT, and this is just to make you understand what and how BERT works and what are its different parts and what are the sort of functionalities that it make use of. So in this lesson, what we're going to discuss is BERT to a level that you can apply it to certain problems. We're also going to discuss some of the problems that BERT can be used in. And without further ado, let's just get started. BERT stands for Bidirectional Encoder Representation for Transformers. So it is a deep learning model that uses transformer architecture to process text data. So BERT is pre-trained on large amount of text data, which allows it to learn sort of about the language and the relationship between the words. And this pre-training step is what makes BERT really powerful, because it's trained on huge humongous datasets. The way we train BERT is combining two techniques. One of them is masked language modeling, and the other is next sentence prediction. So masked language modeling involves randomly masking some words in a sentence and then predicting that word depending on the context that we are provided with. So this really helps BERT to learn about the word and how that sort of a relationship between the words happen and understand the context and so on. In the next sentence prediction, this involves whether two sentences are related to each other or not, that kind of problems. This helps BERT learn about the relationship between sentences and more about the context rather than the relationship between the words. So one of the key advantage of BERT is it can be fine-tuned for specific NLP tasks, and such as sentiment analysis, named entity recognition, question answering. And this really means that BERT can really apply to a wide variety of problems and can really be customized to perform on really specific tasks. Because of its application towards different problems and also its performance, BERT has become the most widely used NLP models, and it has achieved state-of-the-art benchmarks on a variety of datasets. That's a brief about BERT. But when we are using BERT, there are a couple of different things that we need to understand. We would need to tokenize the data into a form that BERT can accept, so which is going to have three different parts. So any sentence that we tokenize using BERT tokenizer, we are going to get three different things, which would be input IDs, token type IDs, and attention mask. So BERT inside makes use of the attention mechanism, and it also outputs in a certain different way. So anyway, what we have on a brief is nothing but it's a language representation, word representation, and a contextual idea of what the words and everything is once we feed into BERT. So, and just because of this reason and the performance that it has produced, the different benchmarks that it has produced, but is going to be a major tool or major model that we have to get our hands on. So now let's just get started doing a project on BERT, which is going to be sentiment analysis of movie reviews, and we're going to implement BERT and make a classifier. Today we are going to look at BERT based sentiment analysis. So for this one, we are going to take the IMDb dataset of 50,000 movie reviews, and the movie reviews are labeled as negative or positive. So the data is ready. So all we have to do now is on Kaggle, what you can do is once you find the dataset, you can go ahead and click on a new notebook, and it's going to load the dataset into the notebook that we create. So we are going to do that. I'm going to name this as BERT sentiment analysis, and I'm going to import all the dependencies right now. Torch import torch dot nn as nn, torch dot optim as optim, import, and import torch dot optim dot lr scheduler as scheduler, and I'm going to import transformers. This is the Hugging Face transformers, and from torch.utils.data import data loader. So this is going to be a classification problem, so it's a sentiment classification, and we'll be able to predict the sentiment of unknown unlabeled movie reviews. And we need to have certain metrics, so I'm also going to import certain metrics that we'll be using. So we'll be using today the F1 score. So from sklearn dot metrics import F1 score, F1 score, and from import, we would need numpy as np, and we would need from tqdm dot auto notebook import tqdm. So that's our dependencies. So I'm going to toggle the line numbers. So it's getting started now. So we also already have done this kind of things. So I'm going to make a config class which is going to have all of our config parameters. So first of all, I need to device equals to CUDA if torch dot CUDA if torch dot CUDA dot is available, else CPU. I need a train batch size equals to val batch size equals to something. I would need a couple of different things. So for now, I'll not define anything else. I will we'll start writing code, and as we progress through, we're going to define different variables that we will require. So first of all, what we're going to do is this is going to be a transfer learning. So we're going to use BERT, and we need to get BERT from Hugging Face, and from transformers we are going to download the pre-trained weights of BERT base. So we're going to use base cased, and BERT equals to transformer dot auto model dot from pre-trained of our checkpoint. So this is our checkpoint, and we also need BERT tokenizer. Auto tokenizer dot we need from pre-trained of our checkpoint, same. Transformers. So this is downloading the model as well as the tokenizer from Hugging Face. So now we have our model and tokenizer ready. So we are going to go get our data. So on this one, we are going to make our data into different folds, so that we would essentially be doing some sort of a cross validation. So we're going to make that we're going to define a fold. So every different data point would belong to some of fold. So on that fold, we are going to iterate through. So we look at it. So first of all, I need pd dot read csv of my the URL to the data. And that's it. And for now, I'm going to let's just say data of sentiment. But previously we have seen the sentiments were like positive and negative, so we need to convert that into a numerical representations like ones and zeros. So list of map lambda x, and we're going to say 1 if x equals to positive and else 0. And once we have written the things, so we can give data of sentiment dot values. So you can see in here x if x equals to positive else. So data, if you look at the data, it's going to be ones and zeros now. So that's perfect. So what we are going to do is now we are going to make folds. So one thing we did not import in here was from sklearn dot model selection import stratified k-fold. So this is something that we are going to typo done it. So so what we are going to do is data dot locate. We're going to make essentially a new column which is called k-fold, and this k-fold we can assign like a random value for that. So let me assign just a -1. So then we're going to sample it, and we're going to sample it the entire data. So it's going to have some sort of shuffle in it, and gotta give a random state, and this random state has to be a constant for reproducing your same result. So config dot seed I would give, and we will write here something called seed. Let's just say it's 5, so we can settle there. And once we have done that, what we can do is once we have sampled it, we need to dot reset index, and we'll drop it. Drop equals to true. So what we are doing is once we sample, our data is going to be really shuffled, and all the indexes will be not ordered. So we want to re-index it and give it an order like 0 to whatever. So that's what this is all about. And once we have done that, I need my labels equals to data of sentiment dot values. Oh, what the sorry, dot values, data dot labels equals to data dot sentiment dot values. So now we'll define our stratified k-fold object, stratified k-fold, and this is of, we'll define n split. So this is the number of folds that we would like to have. Config dot n splits, we can directly pass in this one. So this has to be config dot n split. Same. So we are going to go here and we're going to say n splits equals to, let's just say 5. Again 5. Now we're going to define for fold comma train comma validation data. So what stratified k-fold does is like you can iterate through different bunch of train and validation data that it's going to produce, or at least the index values of train and validation data that it'll be producing. So once you define this one and n splits, let's just say n split is equal to 5, so it's going to produce 5 different splits of train and validation data in here, and if you iterate through, you're going to get the index of all of those values. So you can do a bunch of different stuff once you look at it. So try it out and understand what is happening, and it's going to be really straightforward. And but what we are going to do is something different. skf dot split x equals to our data comma y equals to data of sentiment, and in this one we would say data dot locate value, so the validation data, and it's k-fold, and we would give this to fold. So once we, so this fold is going to range from 0 to 5, so 0, 1, 2, 3 and 4 values. So every iteration of this validation data, we're going to give it, assign it to a fold. And once we have done that, data to CSV, and we're going to copy this path, what we need to do is, and we'll say false dot CSV, and we don't need the index equals to false. So this is going to in 5 we have a typo, I think, config.seed, so we did not run this after this one, I think. Train path size equals to, let's just say train path size equals to 8 and validation path size equals to 8, and task.CUDA dot is, and config, oh that's a small case config, so what's this one, n split, so it has to be n splits, n splits. Alright, has created. Once you refresh it, you should be seeing false. So now our data is going to be this false, so we'll just forget about the original data now. So if you want, what we can do is take a look at the false data set, p.read CSV and we got an additional column called folds, and it's gonna have different fold IDs, fold values. So that's it, nothing any different. So now we are going to define the data class. So review data, I'll call it review data, and define our init function. My data self dot, and so this data is going to be our fold data that we just created, dot reset index. So what we'll do is like we need to load fold by fold. So I would say like get me this fold equals to 0, and we're going to define a separate data loader for each fold. So I could have done it like we have done it in the computer vision problem or anything, but today we choose to do it in a different way, just because we don't want to repeat the same stuff over and over. So we'll try to define some functions for training, and then we'll write a small loop for training. Previously we wrote a really big loop writing everything inside of a loop. Now we're going to put it into different pieces and chunks of code that can be executed inside of the loop. So the loop is going to be a little clean this time. So reset index drop equals to true, and define len self, and we're going to return len of self dot data, and define get item of self comma self comma idx. So review is going to be, review will be, we need to tokenize it. So what we are going to do now is we'll get the reviews. Reviews are going to be in English text. So we'll need to so BERT doesn't really understand English text, but BERT understands a representation of English language, and we have to convert this English text into tokens. So that's the reason why we have imported a tokenizer in here. So we're gonna use the tokenizer and tokenize this review into numbers and different token IDs, to be precise. So that token, every token ID is going to have some sort of a representation or embedding in the embedding layer of BERT. So that's what we are actually encoding this for. So once we do that, we can give this as an input to BERT. So BERT tokenizer self dot data of review and idx of that, and we're gonna say truncation equals to true, and padding equals to max length, and we're gonna say max length equals to let's just say max length equals to 300, and return tensors equals to PyTorch. So sentiment equals to torch dot tensor of self dot data of sentiment, and we're gonna pick the particular index, and it will specify the d type, equals to dot long. Perfect. So now we're going to return a dictionary as usual. So this dictionary is going to contain access. Access would be nothing but, this time this review is going to return a dictionary because we have tokenized it. So once we tokenize, this is going to return a dictionary that contains an input ID, token type ID, and an attention mask. So though we don't really need the last two things, we will only need input IDs. So what we're going to do is we can either take everything or we can just take like the input IDs. We are now here, we could demonstrate taking everything. So what I'm going to do is I need to, when I'm loading the data, I want it simultaneously be moved into the device so that I don't have to worry about it once I'm training. So .do and device equals to config.device, and yeah, and I gotta say for k comma v in review dot items. So it's just a dictionary, so dictionary dot items would just let you iterate through the key value pairs of the dictionary. So what I'm doing is recreating the same dictionary, but this time all the data to be in the CUDA, which means in our GPU. So once our GPU is turned on, every thing, once I'm loading the data, so everything will be in the GPU itself once it is loaded. So what I'm sentiment.do device equals to we get the sentiment, so sentiment.do device equals to config dot dot device. I hope this would not take much time. This is going to be much of a simpler execution compared to the last time. So now we are going to write a class. So let's just call this classifier model or classification model. Just say classif model, and then dot module, and we can define init self comma BERT model. What we're going to do is we're going to take the BERT model that we have downloaded, and we need to create a classifier head into that. So once the BERT model is attached to a classifier head, then our model will be able to make predictions, classification based predictions. So let's just say let's see how we can make that thing. So before that, super init self and what we're going to do is self dot BERT model is what we defined. Self dot BERT model equals to BERT model and all the other stuff. Self dot hidden state or hidden layer, said hidden layer, hidden, this has to be hidden shape. Hidden shape equals to hidden shape, and one more thing, out shape. Self dot out shape equals to out shape. And now we're going to define the classifier head. Self dot layers equals to nn dot sequential of nn dot sequential of, let's just say we can randomly, this doesn't really matter at the moment. This I'll show you. I will create a couple of layers. So now I'm going to do a thing. So point number one is once we input our data into BERT, what we need to take from BERT is its polar output. So the polar output has a definite dimension in BERT, so which is going to be polar out DAM. We can define it like this. Polar out dimension is going to be 768. So this is definite for BERT, but it changes for model to model. For different models it's going to be different. But like model, like let's just say Roberta is going to be of the same size, I think. But if you look at different models, it's going to be different. So this is a definite number, so we got to store it somewhere. So now what we are going to take is once we have written this one, so this thing is directly taking the output from BERT. So this has to be config dot polar out dimension. Just a polar output dimension. So this is going to be polar output dimension, comma, we are directly going to code that into our hidden shape. How did we just say self dot hidden shape? That wasn't really necessary at this point. We don't have to use this thing. Also, we don't have to do this thing. This is it, just self dot layers, nn dot linear, and nn dot, where's my ReLU, n dot so nn dot ReLU of in place equals to true. So we're going to give some non-linearity here, and we're going to give a dropout layer also, and we're going to say dropout probability, let's just say equals to probably 0.1, keeping it as minimum as possible. So now our final and dot linear of hidden state to our hidden shape to our out shape. This is the output shape. Now we have to define forward and self comma batch of data that's coming in, and we're gonna say output equals to self dot BERT model of batch, and out equals to output of polar output. So what we have done is we passed in the batch, but specifically speaking the input IDs of the incoming encoded data, and that is passed into the BERT. And once BERT successfully gives an output, it's going to be a dictionary of a couple other things also, but we are specifically looking at polar output. This is what we want. So once we have our output equals to self dot layers of out, which is something that we have defined. So later this point our model is going to, our data is going to go through all of these layers sequentially, and we're going to return the output, and that's it. And here we can define model equals to class if model of BERT, comma, let's just say 100, and let's just say the final output has to be of shape 2, because we are predicting for zeros and ones, positive and negative. That's it. Let's run this one. We're going to define it as is, and made a couple of mistakes here, and that's it. That's all about our mistakes. Now we are going to write another class called class train. So this is something that's different from all the other stuff that we had done previously. Define init, and we're going to define init. What we wanted to do is, before training, we will create an instance of a class, and we'll make that instance train, sort of. So we'll produce an instance, and all of the attributes like model, criterion, optimizer, scheduler, all of everything, every parameter that would change would be passed into that, and we would essentially change those models and those parameters, and essentially going to output something that's derived from an instance of a class that we have defined. If it doesn't make no sense, we'll look at the implementation now. So model, criterion, comma optimizer, comma scheduler. So our class is going to take all of this thing, and it's going to define. This is also really important when it comes to this one, because all of this parameters, models and criterion optimization, some of the stuff here is responsible for changing the parameters inside the model, and stuff like model is itself responsible for the changes and the weights, and in the end the output, and our model is going to be ready inside the class itself. Criterion equals to criterion, and optimizer equals to optimizer self dot and self dot scheduler equals to scheduler. And now we need to, what we'll do is define fit, and this is going to fit our model, and what we'll take in fit is nothing but a data loader object, and this data loader object will have I believe this is a comma. We'll zoom in a little bit here, and we don't want to see this stuff right now. Okay. Fit self and data loader. So what we need to do, self dot model dot train, and we'll do for batch in data loader. So batch in data loader output equals to self dot model of batch of x, because we have outputted it like that. So x is going to be our input data. So but we are particularly interested in the input IDs. This is what our input is going to be like. And one more thing that we're going to do is we're going to squeeze and that in place, and its first dimension, because the input IDs come in a shape like batch size, comma 1, comma the sequential encoding shape. So we don't really want the one at the first position of the dimension, so we'd remove it by squeezing it. Now loss equals to criterion, and criterion of our output, comma our batch of y. Now the same drill, loss dot backward, and self dot optimizer dot zero grad, also self dot optimizer dot step and self dot scheduler dot step. Okay, so that's how training is done. So this training is for one epoch. Now we need a function to evaluate our model. So that's going to be what we're going to do is predict a metric. Let's just say we already defined like our metric is going to be F1 score. So we want to take like F1 score as a metric and output the results our model produce in terms of the F1 score and the loss after every epoch. So what we're going to do is make a predict metric function. So this method would take self comma a data loader and also let's just say type. This is going to take something called type and we are going to give this train by default. The reason why I'm doing this is I want to predict on the train data and also the validation data, and I want to see if what is exactly happening. I want to return both of the metric on both of the set of data, so the training and validation. So if it is overfitting or anything, we'll be able to catch. So in the end, what we are going to do is not exactly take like the parameter representing one epoch. What we are going to go is in every epoch we are going to go through all the faults that we have made. So if you have 5 faults, we are going to go through all 5 faults in every epoch and we are going to return a combined mean of the metrics, so which would be a good representation. And if we are overfitting or that kind of problem, underfitting, so it would show it. So what we have to do here is define a batch loss equals to, let's just say 0, and if type equals to train, I'm going to say batch size equals to config dot train batch size, and elif type equals to val. We're going to do batch size. Our batch size here is going to be config dot val batch size. Now we'll produce something. Essentially what we need to do is nothing but a loop here also. So in our loop what we'll have is with torch dot no grad self dot model dot eval for idx comma batch in enumerate our data loader. Output is going to be self dot model of batch of x, exactly as we did it for training. Input IDs and we will squeeze them. The first dimension batch loss equals to, it's going to be, let's just say batch loss equals to 0, that we defined here already. So batch loss is going to be summed batch loss plus equals to self dot criterion of output comma batch of y dot item. So now our predictions. So once we have this output, this is going to represent the logits. So we can output this one, but instead we'll need to create or change this back to normal predictions. So once we have the predictions, we'll need to store it somewhere. So for storage purposes, we are going to define threads equals to torch dot empty of the shape len of data loader comma batch size. So if we have defined it for train, it is going to produce a tensor of this much length, and the batch size specifically for train batch. So when we are predicting the train, it'll have a container of train batch size in it. And also we need to labels equals to torch dot empty. It's going to be exact same tensor though. Len of what we call data loader comma batch size. Now batch loss is this much, and heads of idx comma everything, this must be equals to the prediction that we make from the logits, the outputs of the network. So we'll need to make a function. So I need to make a function of a static method at static method, and I'm going to define logits to predictions, logits to prediction of, this is going to create the output. Okay, so our preds is going to be torch dot argmax of dimension equals to -1, that's for sure. And inside we are going to say torch dot softmax, again dimension equals to -1, but this is going to be output dot detach. Output did you say output? Yeah, output dot detach. This has to be detach dot 2. I want this to be in CPU now, CPU, so that the sklearn can compute some metrics out of the predictions and the labels. And I'm going to return threads dot view -1 comma 1. Also I'm going to define return metric of threads comma labels. I just want to be on the safe side, so So I'll do return config dot metric, which we'll need to define on config, because we have imported the F1 score, so the F1 score can be a metric. F1 score. So now that's defined in there, config dot metric, and threads dot to our predictions are already on CPU, but we can give dot to CPU again, doesn't really matter. So just to be really safe, comma average equals to weighted. This is what we're going to return in this function. So now once we have the predictions, I mean the logits, what we'll do is we'll need to give that into the predictions. We need to output it as the prediction. So self dot logits to predictions of output, and also labels equals to labels of id x comma everything equals to batch of y dot to CPU. So we can say metric equals to self dot return metric of threads comma labels, and finally we can return metric comma batch loss divided by len of data loader. Cool. We have defined one method here. Oh, so this is also a static method. So we have 1, 2, 3 and 4 methods defined in here. One for prediction, the other one for training, the other one for prediction. So that's it. Now we can write the training loop. False equals to pd dot read csv of, we're going to import the data. I'm going to change the data into model.to config dot device, and we changed it to whatever the device available. Now criterion for this one is going to be cross entropy loss, nn dot cross entropy loss, and optimizer, that's going to be Adam, optim dot Adam of model dot parameters comma lr equals to config dot lr, which I think we have not given yet. lr equals to name -4. Now we need to do scheduler equals to optim dot lr scheduler dot step lr optimizer. For lr scheduler we need to pass in the optimizer, and we need a step size. Also we would require a gamma. So what happens is, once we are given, let's just say we are given gamma equals to config dot gamma, okay, gamma, and our step size also equals to config dot step size. So what really happens is, in the specified number of steps that we give, let's just say 10 steps, so it's going to look at the number of epochs. So once this equals to actually the number of epochs, this is going to get in action. So the learning rate that we have defined earlier is going to be reduced by a factor of config.gamma in config.step size, number of steps or number of epochs. So step size and gamma has to be defined here. Step size equals to say 10 epochs, I want my gamma to reduce by a factor of 0.1, and config dot step size and config dot. So now we'll initialize train equals to train of model comma criterion comma optimizer comma scheduler. And add them. Fine. So now what we would need is a small loop. So within that loop is our optimization is going to be based on. So we'll write this loop here. For epoch in range config dot epochs. I believe that I have written it in here, the number of epochs. No, epochs, let's just say 5 epochs. That's what we are going to run. Config dot in range config dot epochs. We can also wrap a TQDM here so that we'll know the and train data equals to data loader of review data. Do you remember the review data? This was the review data loader. So every time we are on an epoch, what we'll do is we'll also be in another loop for fold in range config dot n splits data loader review data it's a big D, and review data of false dot locate false of kfold. So what I'm doing is I'm making a specific data loader for a training and validation. So for training, we would say we want everything except something, the data a k fold equals to fold, and batch size equals to config dot train batch size, config dot train batch size, and drop last equals to true. And the same goes for val data as well. So data loader of review data of folds dot locate folds of k fold equals to fold, comma batch size equals to config dot val batch size. I believe we have defined it. And again, drop last equals to true. And now we'll define a couple of things here. We need to have after we have defined the number of epochs, we are in the loop. What I want is train loss equals to something, an empty array, so val loss equals to this thing, and train f1 score equals to the same, and val f1 score equals to the same. So this is going to return all the data, all the matrices that it calculates in each of the folds. So once we have, let's just say 5 folds, so all of the fold results of the folds will be saved into this one. Now we can take an average of this one to represent the average epoch loss or f1 score or anything of that sort. So we are going to average this thing later. Val data. So now we'll call train dot fit train data, once we have made train and the other data, validation data. So train loss that we get dot before that, now we have fitted. Now we need to do train dot predict metric. Yeah, so predict metric of train data, and we need the mode to be train, and this would return the metric, which is the f1 score, and also a loss. So now we are validating on our train data itself. T loss. Now we'll say train loss dot append T loss, and train f1 dot append what tf1. Now we'll do the same for the validation as well. vf1 comma v loss equals to train dot predict metric and val data. We need the validation data data loader, and we only say val. So val loss dot append v loss, and also val f1 dot append vf, where vf1. Okay, so that's it. Now we are going to define 4 more other things which has to be defined in here. So in the metric that we need to calculate is epoch train loss, and this is going to be epoch val loss equals to, now epoch train f1 equals to this thing, so epoch val f1 equals to this. So this is per epoch, this is, the other ones were not per epoch, the other ones were this also per epoch, and the other one also is like per epoch and per epoch. And once we have the matrices calculated from inside of the loop, we can epoch dot train loss dot append np dot mean of train loss, and the same way epoch train f1 equals to epoch train f1 dot append np dot mean of train f1. Now again epoch val loss is going to be dot append epoch val loss dot append np dot mean of val loss, and epoch val f1 dot append np dot mean of val f1. That is it. And once we have this thing, this will essentially train our model, and we can import matplotlib dot pyplot as plt, and we can do plt dot plot of range config dot epochs config dot epochs comma epoch train loss. We can plot everything: epoch train loss, epoch val loss, you can say epoch val loss, epoch train. Now f1 score comes in, f1 score. Now epoch train epoch val f1 score, val f1. So I want to make it like epoch val loss. Okay, epoch train. Okay, f1 scores and the others. Now I'll do plt dot legend, and I'll pass in train loss, comma val loss, train f1, comma val f1, bbox 2. I can give this comma locate equals to upper left. So that's it. If this runs successfully, then our everything is over. So what I can do now is I'll test it on this one, a small data set, which is going to be n rows equals to 50. I'm just going to take like 50 data points and create a new data set with it, and I will try to check it out. Okay, comma. This is defined now. And we should be able to run it. So I'm not going to run this thing. Instead, what I'm going to do is give this on a limited data set. I've demonstrated running on a limited, very limited data set. So I'll run it from here. So it's going to run. And once it's done, we can plot it as well. We can see our GPU working here. So obviously our results are not really great, but one thing to be said is the values that we have plotted here, epoch, train loss, and so on, these are all cross-validated values, so you can 100% rely on them. Since we have only used 50 data points, we got 50k data points here. Make sure you use all of them, or experiment with any subset of the data, and that's it. And you can even customize this thing to the metric function that we have created, the static method we have created in here, to give any function in the replace this f1 score by recall score or precision score, and that's it. It's gonna return that score here, and that graph here. You just have to change the names as well. So that's it. With this, we'll wind this up. Welcome back, and for a quick moment we are going to look at how we can upload a dataset on Kaggle. So what we have to do is open up Kaggle, and you're going to see this sort of a window, and this is your home page, and you're going to see a lot of works and stuff in here. So go to the top left corner and click on that create button, and you're going to see three options pop up, and one of them is new dataset. So click on new dataset, and you're going to be redirected to another window, and data that you have, just drag it and upload, and it will start uploading. And once you upload it, you just can give some sort of random name. I don't mean random name, just give a name that's related to the subject of the data that you uploaded. So once the data is uploaded, you have the option to make it private or public. So you can do either ways, it doesn't really matter, and just hit that create button, and it's going to create the dataset for you, and you'll be able to access the dataset from different kernels or dataset part of your profile as well.